Well, I think we're ready to get going. Any questions to start us out today, folks? Okay, the recordings are getting a little bit trickier on Zoom, so let's take a look at what the annotation looked like before it got wiped out. This is pretty much our announcements to start out our day today. We're going to be finishing off section 6.2 probably rather quickly. We'll spend the rest of our time looking at our definition of logarithmic functions and working with them initially. And that's going to be the last section, 6.2, or excuse me, 6.3 that you could expect on our third and upcoming exam. So exam 3 is going to be next week. It starts off at section 5.5, goes all the way to section 6.3. But I'd say this is an exam where it'd probably be well worth our time to spend all of Thursday. That's supposed to say review, not view. We'll spend all of Thursday reviewing for this upcoming exam. That'll be time definitely well spent in our schedule. And one reason for spending the extra time is there is a couple sections that are just a little extra tricky this time. That's section 5.5, really about polynomial theory, the zeros of the polynomial functions, the rational roots, theorems, things like that. We want to really go over again just to get a good feel for it. And section 5.7, that one's not too bad, but it gets a little bit hairy when you're talking about vertical asymptotes, horizontal asymptotes, x-intercepts, y-intercepts. Putting that all together to graph a rational function, it just takes time and practice. So we'll take that extra time when we come back on Thursday's class on this document. Then there's a bunch of other review notes that are available. Just to have some sense of parallelism, I posted this document again. So out of our textbook, it was a free textbook, so it's not the best problems in the world, but that's a great source of additional problems to take a look at. Version 2 of the sample exam, this one is just going to be the blanked out lecture notes. You can treat them as pretty much worksheets now. And sample exam 3, I'm going to leave this one entirely to folks in the class. So this one is for yours to study on your own. I'm going to be having all the solutions posted on Sunday, probably early Sunday afternoon, so that if you work on it a little bit earlier, you'll be able to check out all your answers on Sunday, on that day there. So this sample exam is a little bit longer. And if you open up this one, this is pretty much how it looks like. It's a bunch of problems on a list. And it goes all the way down to problem number 22. Not every single problem is going to be a really, really amazing exam problem, but it's definitely helpful for studying. So I'd say out of all of these, the one that's maybe the slightly weirdest, let's see, let me see if I can find it again, might be, well, they all look pretty good. One looked a little bit weird this morning. I was kind of debating on taking it off or leaving it on there. No, I think they all look great. The one that seems maybe a little bit far off is maybe problem number 22. It's not something I'm directly going to put on exam, but it's definitely going to be helpful since we need the facts that you're going to get off that problem number 22 as well. So think of this as one really, really big worksheet. We'll have the solutions posted on Sunday, and it'll just be dropped right under here, an extra file that says solutions to this worksheet here. I put on the notes, I would say this one is definitely highly recommended to go through. If you can solve all of those problems cold, you're going to be in really, really great shape for exam 3. And the reason I don't have the solutions just yet is sometimes a really, really good strategy for practicing these things is definitely try to solve them without access to the solutions. That way you'll know exactly which problems we need to work on a little bit more than some of the others. And so when you go to work on this document here, I'd say don't even have anything available. Solve it cold like it's a real exam, maybe even set a timer. That is probably less necessary. But solve it cold like it's a real exam, and just circle any problem where you felt like, dang, I don't think I know that formula too well, or I'm not too sure how to start this one. That's going to tell you which problems you need more time on, which formulas you need to spend a little bit more time on memorizing. It'll be a huge help. Then again, you'll have everything posted for the solutions on Sunday. Well, that's my spiel of announcements so far. Any questions or comments at the moment? Okay, another thing that we got in the habit of doing right before an exam is I changed all the due dates to every single one of these sections. Well, I didn't really change the due dates, but I just put a global extension to everyone in the class. Those sections from 5.5 all the way through 6.3, even though not all these are due yet, but they all have an extension of 15th of November. And I've had some weird issues putting in extensions on ALEKS. Sometimes I think I did it right and it didn't go through and I get emailed again or asked about it. So if it looks a little bit off in your account, if you can't get into that section, just send me an email and I'll try again. I'll put it in again and hopefully it'll take the next time. Well, after that, I think my only other big announcement is definitely don't forget your calculator. Try to remember to take the calculator that you usually come to class with or work homework on. I'll have spares, but you definitely probably wouldn't want a spare calculator if this is not the one you're used to using. That could be a big red flag on an exam that we don't need to get to worry about while you're trying to solve these problems. And I think that's finally the end of my announcements. Any questions or comments whatsoever so far, folks? Okay, well, let's turn back to the Moodle page. We're in section 6.2, and let's see just what else we have to get through on this one. It's all about the graphs of exponential functions. And this is really all we've been doing, graphing these functions using the point plotting method. So nothing too amazing or crazy so far. There's actually more formulas in section 6.1, the ones about compound interest, as well as continuous compounding. But here, we're just using ordinary point plotting methods. When we graphed 5 to the power x as an exponential function, that's the graph we obtained here. We observed it has a horizontal asymptote. So that's the equation, y equals 0, that they asked for us. Draw the asymptote with a dashed line, so we just overlaid it on the x-axis that way. The domain of this function is all real numbers, and the range, because it has a horizontal asymptote, and this one is a barrier for our function, the range is from 0 to positive infinity. So you will take on every single real number that's positive going up in that direction. So that's our work so far. Any questions at all, folks, on that first plot that we produced? Okay, then the next one we plotted on Thursday wasn't too wild. That was the only thing that's new. A negative power there causes a reflection about the y-axis. So 4 to power negative x is now a exponential decay type of problem. It's decreasing the whole time. But still the domain is negative infinity to positive infinity. The range is from 0 to infinity. And we made a remark, the domain doesn't change on these functions. Only way to really break it and change the domain is do something weird up here, like put a square root on that x, but now it's not any longer an exponential function, it's a function composition. So these things have domain all real numbers. The range, however, can change on these functions, but we would have to do some weird transformation, like say, this one right here. Because of that -2, it's going to change the graph by dropping everything down 2 units when we go to plot it, and that's going to affect our range, and it'll even affect the horizontal asymptote. This one is at y equals 0, but if you put in a -2 right here, let's collect this thought right away. Actually, that was a good color. Let's see if it has that color. Because of that -2 right here, our horizontal asymptote is automatically a y equals, we have to lead with a variable y to make it a horizontal line, and you just grab that value directly, y equals -2. So that's a nice upper hand. You can just look at the function and just determine immediately if there's something being added or subtracted. You have that as your equation of the horizontal asymptote. We might as well just start by plotting that thing. Once I can get this. Oh geez, there's my 4th try. I don't have had too much coffee today. They don't have the most steady hand, but we'll get through it. So here's -1, -2. And we got the first part down. We have a horizontal asymptote. Now, next thing we could take a look at is that sign right there. That's going to cause a reflection, and this one's going to be about the x-axis. So it looks like all of our information, the whole curve should be below our curve right here, y equals 2, and the x-axis as well. So that's causing a reflection. This is dropping it down by 2 units. And so our whole curve is somewhere in this location. To get the rest of the plot, it asks us to do 5 points. That's the same as the instructions in ALEKS, so we're doing it the same here, just so that we have a bit of solidarity with those instructions. This is really probably the major meat of this whole problem, because we're doing lots of exponential notation when we go to do these values. Probably a good first choice might be something like -2 for x. Then y is going to be -1/3 of that value of x minus 2. So lots of practice right here with exponents, and that's definitely good practice. We'll plug a negative 2 right inside here and get negative 1/3 to power negative 2. Oh, and I already made a mistake, darn it. I think I see where my mistake came in. I carried the negative into that location when I tried to recopy the function, but it should be like this instead. So sorry for that mistake, starting out on our first question of the day. That's a little bit frustrating. Let me highlight it in yellow. The negative sign should be right there, not inside the parentheses. In fact, that would invalidate our function. Our base had to be a positive number, not equal to 1. So you can't even put a negative sign in there. It's no longer an exponential function at all. So back down over here, let me correct it in this location. Should be a negative outside the parenthesis as well. And then finally, minus 2. Okay, all I was meant to do is put a negative 2 right where that x is, but sometimes copying the whole thing down is part of the battle as well. Now we can start working this through. First thing I would deal with is that power of negative 2. This will flip the whole fraction. It'll be 3 divided by 1, so just 3, to the power of negative 2 minus 2. Then 3, oh, that's a positive 2 once we flip the fraction. Then that 3 squared is going to turn into a 9. So now it's negative 9 minus 2. I'll get a negative 11 off that first row right there. That one was kind of a battle. Does that look right to folks on negative 11? Okay, so with negative 2 down, it gets a little bit easier after you've done it once. Let's go off now to negative 1. Again, all I'm doing is putting a negative 1 here. So let me carefully this time copy in negative 1/3, power negative 1 minus 2. Then back over here, I'll lead with the negative sign, and then take the same strategy. If you flip that whole fraction, make it 3/1, which is the same as 3, you just have to write in your exponent as positive. But 3 power 1 is still 3, so even if you took off that exponent, that'd probably be just fine. Then minus 2. This is a glorified negative 3 minus 2, so it becomes negative 5 in that value. Then rinse and repeat. Throw in a value of 0. 0 goes in right here, and now it's getting actually a little bit easier to run through. If that value is 0, well, anything non-zero to a power of 0 is automatically a 1. So we're just staring at a negative 1 right there on paper. Let's also collect the minus 2. Now this time we're not flipping the fraction. This turns into negative of 3 to the power 0 became a 1. So this one is a glorified negative 1 minus 2, and we have a value of negative 3. Let's extend that a little bit lower. Then finally, let's put down a value of 1, a value of 2. That would definitely be 5 points. So we can let the graph end once we get these next 2 values. Any questions so far, folks, with these 3 rows down? Okay, 2 more to go. We'll plug a power 1 right here. Power 1 is just as nice as a power of 0. If it's to power 1, you just get the whole 1/3. So it's negative 1, 1/3 power 1. I'll write it that way just to connect the dots, showing that step. And now it gets a little bit annoying. This is now negative 1/3 minus 2, but now it needs at least common denominator. Let's multiply this by 3/3 to get negative 6/3. Now it's a negative 7/3 altogether. And 3 goes into 7, negative 7 twice, with a remainder of 1/3. So we'll plot something just slightly below negative 2 when we go to put in that value at a positive 1. Next, for a positive 2, it becomes negative 1/3 power 2 minus 2. Then back down over here, if you're raising something to a power 2, you're just squaring the numerator and then squaring the denominator separately. So this will become, first the negative sign out front, up above 1 squared is just 1. 3 to the power 2 becomes 9. Minus, now this one, think of multiplying it by 9/9, so we'll have the same common denominator. And now it's a negative 18/9. Always good to double check that. 9 goes into 18 twice, so we really have the negative 2 from the last step. So now it's negative 19/9. And 9 goes into 19 twice. Negative 2 times for negative 19. with a remainder 1, but it would be a 1/9 as a mixed number. And if we did it at 3, we would get something like -3 and 1/27. If we did it at 4, we'd see that pattern just keep on emerging, where the fractional part of the mixed number is just getting smaller and smaller and smaller, meaning we really are heading off to that horizontal asymptote. So all that's left to do is plot the whole function using this information. So let's go down the line. I guess we need to put values down too. So this will be -1, -2, +1, +2. And now I kind of forced my hand. This is the scale in the vertical direction. I'll just try to make this all fit. So -3, -4, -5, -6, -7, -8, -9, -10, -11 we have. So that should be a decent scale for us to run through the whole problem. So finally, this is the fun part. We're connecting dots. We have a dot at -2 down to -11. So there's the first point found on the graph. At -1, we're at height -5. So there's the next point. 0, we take on the value of -3. So we are right over here on the y-axis. Now we have a y-intercept. And these are the hard ones to plot. At +1, it's at -2 and 1/3. So right over here, I'm at -2, -1/3 would drop me about right there. This one's even harder to plot. At 2, it's -2 and -1/9. So I'll just draw it about like that. It's almost impossible for me to get these in exactly. So just make it look close and believable, and you'll have a great sketch. Then last thing, the curve is, let's make it actually look exponential. Usually it looks almost vertical on your last point you put down. Then it heads towards the asymptote, gets closer and closer. The way I draw it, it looks like it's actually hitting the asymptotes, but that's because I can't magnify this enough. There is always a separation between y equals -2 and the curve g of x. So it goes down in that direction forever, and that's finally the graph of y equals g of x. Definitely a process. On the real exam 3 that we're going to be taking a look at, you should be prepared to do one of these, but I'm not going to put a bunch of them on there since it takes a while to do a single one of these. It's a lot of plotting. And it probably won't be as noisy as this problem. It should be a little bit easier to run through. So if you can do, say, parts A, B, then you're in great shape. Try out this one like this, part C, and some of the review problems, just to get extra practice. Well, let's take a look. We plot the function using 5 points. We have the asymptote as a dashed line. All we need to do is state domain and range. So for this portion, domain is automatically a freebie on this. It's all real numbers. And we can see it just looking at the graph. Sure, it's going down steeply in this direction, but you can plug in any number. It's really going to the left forever as well. And it definitely looks like it's going to the right forever. So the extent of all the x coordinates are from -infinity to +infinity. The range, though, does change on this one, like we mentioned. Any volunteers for saying what the range must be on this problem? Exactly. And I like the way you said it. It has to be go down and then up. So the extent of all the second coordinates will be -infinity all the way up to -2, but it never actually hits that -2 like we've been mentioning. And we have to say that with a parenthesis right there. So good call. That's the range of this function. The range are going to be all the values that you could actually set g of x equal to and try to solve it. So the moment you know that there's a range, you can also say this. G of x equals any number outside that range, any number whatsoever, even say a -2, has no solution. To really solve an equation, you have to pick something out of there, maybe -10, and then we could make that happen. But then again, solving these equations are extra tough. We don't have the inverse function. We'll be getting back into equation solving in the next section, and after we develop more and more information about logarithms. But we did it, folks. That's our first graph to get started on Tuesday. Kind of a rough first problem, but we made it. Any questions at all on the conclusions here? Okay, well, yeah, go ahead.
So with gx equals -2 has no solution, that's similar to what you have on the first example where it says like 5x is less than zero, or sorry, greater than zero.
Exactly, yes.
For all x, so is that basically kind of along the same line?
It is, absolutely. So we said here in the purple, 5 to the power of x has no solution if we set it to 0, only because it's missing from the range. Exactly. And on this one, same kind of issue. We can't put 0 in there, but I was focusing mostly on the boundary point because it's surprising. Can't even solve that one, even if we tried. As strange as it is, just missing from the range. Other questions so far? Okay, well, some of the related topics that we're going to be looking at go a bit like this one. This is a problem that I stole mainly because it's there in ALEKS. I think this is kind of the weirdest ALEKS question, but it's really not too bad. In the actual ALEKS system, all we're going to do is use a tool to grab the curve and drag it around to make it land on the right place. It says below is the graph of f of x equals e to the x. Let's just label it to be specific. This is y equals f of x on the red curve. We want to, and these instructions are verbatim from ALEKS. It's kind of weird the way they say it. Translate it, we're not a translator, but what they mean is move it around to make it become the graph of g of x. And what does g of x do? It's a 3x plus 2 minus 4. Let's blow that up down here. So it's power 3. Oh, and I think that is a typo. I didn't necessarily want to power 3. I want to match the e right there. Sorry about that, folks. That should have been an e. I mean, it was close. E is about 2.71, but it's not 3. Let me put that in red right here just to show that correction. So that should have been e to match the e that came from this. If you change the base, then this becomes not a very good concept anymore. There's more going on. So now it's back down here, corrected to e to the power, x plus 2. Then minus 4. And we already dealt with something like this, the minus 4. We know the whole graph should just go down by 4 units. I'll just say down 4. So you can visualize this curve, just literally drag it down by 4. But then the plus 2, again, that always kind of messes up what I expect to have happen. Any volunteers for what should happen with that plus 2? Should it go to the right 2 units or should it go to the left 2 units? Good call. It should go to the left if it's on plus 2 right there. So this goes in the opposite of our expectation, left 2. So we go over here. We're going to take this whole curve, drop it down forward, left 2. And a good first point to move might be this one. This is its initial value. So it's going to be going down 1, 2, 3, 4. It's ending up at negative 3. But our curve y equals f of x has even more going on for it. It has a horizontal asymptote at equation y equals 0. This is not something as important for us, but for doing this on paper, then it's a good idea to plot the new asymptote. If it was at y equals 0, then it will go down 4. It really does go left 2, but it's infinitely long, so moving it left 2 doesn't have any meaning for a horizontal line. It's all about the down 4. So the new asymptote is all the way down right here. So we have an asymptote at y equals negative 4. We have a point here, and that's enough to sketch the whole graph. If we were trying to do our normal graph, we'd probably do more points. But this topic coming out of ALEKS, you're just grabbing the red curve, moving it down 4, left 2, and that's the whole thing. Oh, and I did make a weird mistake. I did move it down 4, but let's also move it left 1 unit, 2 units as well. So here's 1, 2, 3, 4, 1, 2. That's a new location of our curve. Then the rest of the graph should look about the same as the one in red. Trying to draw it with the exact same shape. A little bit easier on the software because when you drag the curve around, it drags with that exact same shape. But that's a new location of y equals g of x. We moved it down 4, and then at the last minute, we were called also move it left 2. I mean, we said that. I think I got sidetracked with the asymptote. And that's what the new graph would look like. Any questions about that one there? at the moment? Okay, well, we've done it. This is dealing with graphs, translating graphs. The one thing that we've done a lot of work though is whenever we had a quadratic formula, occasionally they gave us a graph and we found its equation. We did the same with the rational equation. And on this problem, example 3, they did a little bit differently. Instead of giving us a graph, they gave us a table of values or pairs for an exponential function, and we need to write an equation for that function. So this is the second topic in ALEKS that I think is a little bit weird. We should be ready to go with. So if you see this in the ALEKS system, this would be a great place to come back to in the notes. First thing to do is let's just write down the function. They said it's going to be exponential, and I trust them. So let's write it out as f of x equals a times b to the power of x. So that's how our exponential function is always determined. The value of a, we call it the initial value. And just by inspecting the table, we can find the value of a immediately. Anyone spotted what a should be equal to? Exactly. The initial value is this right here. The way we can tell is because of the 0. So that's the initial value. So right away, we can say next, f of x equals 1/2 times b to the power of x. And one thing that might be a concern with this is you might ask, what if they didn't give us a 0 for initial value? They definitely don't have to, and you can still solve this whole thing. So if they never gave us a 0 and we still had to find 1/2, then we would just write down, say, f of 1 equals something, f of 2 equals something. We come up with 2 equations, and we can use those equations to come up with the 1/2 right here. So that's a good process to think about for getting through these problems. I think in ALEKS, they always give the initial value, so I'll leave it up to the class. We can find out how to solve it like this later on after we solve this problem, or take a look at it right now. Any volunteers for one way or another? I'd say on the exam, I would definitely give the initial value for sure. Let's keep it that way. I think that's a good way to go. No reason to add extra noise when we're studying for upcoming exam. I agree. So this is very common to give. Definitely on exam, I would give it. And this is all you have to do, plug in the 1/2. But what I'll do on the notes is I'll come back to this. This is now a note for me. And I'll put in this information just in case it does come up in ALEKS. So if you get a weird problem in ALEKS, this is a good place to come back to. I'll show how to get the right information even if a 0 does not occur. But now that we have the 1/2 value, we still have to solve for b. And the way I'm going to solve for b is kind of how I was indicating up here. So this is something that we would have to do, but it's not really terrible. We used up this row, so just go to any other row and we can solve for b. You can use f of 1 equals 2. It's probably a good call because those numbers are easier. F at 2 equals 8 is also going to give you your b value, and same with this row. But why work hard, right? On a real exam, you want to pick the method that's going to be fast, involve the least amount of steps, and plugging in an x equals 1 is always the easiest way to go. So let's call this step 1. Pretty much that's all we had to do is use the initial value. But now my second step, I'm going to use this row, f of 1 equals 2. Once we write down that equation, we're using function notation, so the 1 is going to go right exactly here in the function that we're building all along. So now we have a 1/2 times b. It's now raised to a power of 1. And the whole thing is still equal to 2, but we're solving an equation for b, so that's basically done, right? Multiply both sides by 2, and b would be equal to 4. So then our last step 3 on this is really just putting it all together. If this was a real exam question, we still have to state the completely assembled function. So go from right here, f of x equals now, let's go back to the green on that just to highlight where it came from. A 1/2. We found a value of b is 4. So now it's times 4 to the power of x. So that's a entire function, and it's pretty fast actually. Coming up with an equation of a function like this is honestly faster than if the function was linear. That's a little bit weird. If I give you 2 points on a line, then, well, if I give the slope, it's about the same process. But if the slope is missing, it's worse than this. This is a really fast way to get a function out. And it's so fast that it's worthy of doing a 4th step on this thing. It's just a check though, so nothing special. Our answer is really right here. Let's box it just to emphasize it. But the check is so fast that you could save a whole minute on an ALEKS problem by doing this check. And those minutes do add up. I would do this. We've used row 2, we've used row 3. Let's see if we use the last row, we really get an 8. So f at 2 had better be 8, but this is a check. So we're plugging 2 right here in our answer. It's 1/2. Now 4 to the power of 2 in that check. So it's 1/2, and 4 squared is 16. But 16/2 is 8. So that tells us, yeah, we got the right value when we plugged in a separate value into our function. Doesn't complete the check, right? If I really want to complete the check, I'd plug in a 1, a 0, a -1, but that is becoming less and less helpful. If you got 1 extra row right, that's really strong numerical evidence. You probably did the whole thing right. So I'd usually just check 1 additional row. Well, that concludes these notes. 6.2 is a pretty short section. 6.3 is also pretty short. When we get into 6.4, 6.5, 6.7, those are the last sections of the entire semester. So congratulations, folks. We're almost done with all the material. Those sections take a little bit extra time to get through, but we are in really great shape for completing the course and having a review day as well for the final exam. Well, any last questions then, folks, before we close these notes and go to the next section? Okay, let me save these. And now we're ready to define logarithms. We're going to do one more plot really fast just to kind of illustrate what a logarithm looks like when we graph it. But it won't be the plots like we were doing on these notes. It'll just be based off pretty much 1 or 2 points. And here's our next section. Now this section is a little bit weird because we're dealing with the inverse function the moment we mention logarithms. And because inverse functions are coming into play, there's a lot of stuff that we have to say. So I'm going to do these notes a little bit different today. Here's the core definition that we need to define a logarithm. But before just staring and reading this wall of text, let's actually focus right here first, and then we'll look at the definition as we move through each piece of this. We're going to find the inverse of this exponential 3 to the x, look at its properties, look at its graph, domains, and ranges. Then we'll cite the definition above once we get a better feel for this. Just that way, we don't have to deal with everything all at once. First thing to ask us is to sketch the graph of 3 power x. If you ever need a really fast sketch of a graph and it doesn't say like use 5 points or something like that, pretty much this is all you have to do. It wants a dashed line for the asymptote, so that's probably the only real annoyance here. Here's y equals 0 for our asymptote. Now 3 to the power of x, immediately, if you put 0 in there, you get a 1. So it'll cross exactly at 1. Now let's put in a value of 1 as well. Put 1 inside f of x. It doesn't hurt to actually write these on the margin. F of 0 became 1, and I'm going to plug in a 1. F of 1 is just going to be a 3. Let me try to make those a little bit better. So here's my second point. And because we have enough experience on what the whole graph should look like, really shouldn't be more than even a single point. So let's go over here. Attempt to draw that horizontal asymptote, or the curve around the horizontal. Also, draw the curve around the horizontal asymptote in a believable way. Sorry, that was a weird word salad. That's hard to get through. And then you're in great shape. So that's our y equals 3 to the power of x, or y equals f of x. So we have everything. We don't have the domain and range, so let's state that down below as well. because we're going to be dealing with the inverse function, let's state it as domain of the function f, still all real numbers, much like a polynomial, but the range does change. This one's not all real numbers. It goes from 0 up to positive infinity. So that's the function we've been studying since section 6.1. And now they ask us this information. Explain how you know f, we're talking about f of x is 3 to the power of x, is invertible. Or in other words, how you know f inverse, that symbol there, really exists. This is really a review topic. It's going back like well over a month. Anyone recall how the graph alone proves the inverse exists? And no worries if you're not sure. Again, this was some pretty far back information. If we're not sure, here's what I would do. Sorry, go ahead. Exactly. It's all about that horizontal line test. If a horizontal line intersects your function more than once, it is not invertible. But if every horizontal line can intercept at most once, then you do have an invertible function. I'll delete this in a moment, but yeah, this would pass a horizontal line test fantastically. Every horizontal line above y equals 0 intersects exactly once, and there's no possibility to get a second intersection. So let's just say that's right down below. Since every horizontal line intersects the graph of y equals f of x at most. This is the most important thing of the horizontal line test. You have at most one intersection. So at most once, f passes the horizontal line test. And I really thought I could fit that all in there. Let's get some extra space. And so f inverse exists. That deserves an exclamation mark because the inverse is now the logarithm function. Well, any questions so far, folks, with the information here? Okay, now that we know the inverse exists, part C is telling us the inverse function is denoted this way. It's a logarithm to the base of 3, and we write it this way. Let's just put it in pen so it's more readable. F inverse of x. If you started with an exponential function to the base of 3, it's going to be equal to log, to stand for logarithm. We put the base as a subscript. So if this was the line on your paper, on lined paper, drop it a little bit lower. Then we put of x just to remind ourselves we're dealing with the function. But the parenthesis around the x, as long as there's not multiple terms going inside your logarithm, often it's actually dropped entirely. People just might write, say, log base 3 of 9 or something like that. So we have a base that came directly from here that will always match up. And this is read as logarithm of base 3 of x. So that's our inverse function. It says that's our inverse function. Use dashed lines for the asymptote and sketch the graph of this function, state the domain and range. And putting the sketch down here is kind of what's expected, but it is better to put it right up here because it's a little bit a better way to illustrate what the function looks like if we plot the function and its inverse always on the same set of axes. The reason we do that is there's an intersection that goes through, or excuse me, a reflection that goes through this line. Here's y equals x. This one is not an asymptote on the graph, but if we take this curve, reflect it across y equals x, then we're going to get our new graph, the one for the the one from the base 3 logarithm down below here. So let's start getting points. And what I want to do is, let's also take a look at what we did back in the day, just for the sake of reminders of how the rest of this is going to go. So when we did this kind of plot back in the day, it was all the way back in section, geez, it was way while ago. It was in September, it was a little bit warmer then. We first look at the horizontal line test. This tells us if our function is invertible or not. Then finally, when we were doing, say, these kinds of plots, they gave us two functions, or excuse me, they gave us one function, a graph of f. This was the original y equals f of x. We stated the coordinates. One of them was, say, 5, 3 in this location and so on. And then when we want to graph the inverse, we said it reflects across y equals x, but the real thought, probably the best thought with inverse functions is swap your x's and y's on everything and you're in great shape. That's exactly what we did. We swapped all the coordinates. We swapped domains and ranges, and we're even going to swap asymptotes. If there was a horizontal asymptote on that graph, it'd have been a y equals. It becomes an x equals and turns into a vertical asymptote just out of nowhere. So let's apply all of that to this graph right here. So we'll put our logarithm. Let's plot it with a special color. Let's go maybe green. Right up here on the graph, just to show both at the same time, we do have pairs of points here, so we can put on the graph as well, f inverse of something equals something. But that's a y value, so that y value becomes the x value inside. The x input becomes the y output for the inverse function. So now it's saying f inverse at 1 is 0. And this is true for every single logarithm. It's pretty much a property of logarithms. At 1, they always take value 0. And for an exponential function like this one, at 0, it always takes a value of 1. So we have a x-intercept right exactly here in our natural logarithm. We swap another point. We're just trying to get a fast graph. So now f inverse of 3 will be equal to 1. So I just took the 1 here, made it at the output, took the 3, made it the input. So now if we go all the way over to 3, 1, 2, 3, we're at height of 1. So what exponential functions do is, as you read them left to right, they're growing extremely fast. A logarithm, when you read left to right, they're growing extremely slowly. They grow so slow that it almost looks like there's a horizontal asymptote on your paper, but there is none. It just has an extremely slow rate of growth, being inverse to the exponential. So the rest of the curve is going to look like this. It comes up and around, about like that. But notice I'm trying to draw it as if it has a vertical asymptote, which it absolutely does. The vertical asymptote would look like this. And this would be the equation x equals 0. So this is our first entire plot of a natural logarithm. Excuse me, I keep saying that. Of a logarithm base 3. We have an entire section on doing these kinds of plots. Again, the major reason why we want to do this is just to take a look at the definition above and have a picture that we really filled out. So this is y equals log base 3 of x and is inverse to 3 to the x. And that's all the things that we would expect for an inverse function. It's a reflection across y equals x. We can say down below here, the domain of the inverse function. Anyone happen to know what it must be immediately? Exactly. The domain is the set of all x coordinates, but we're swapping x and y. So if we talk about the domain of this, we grab the y coordinates of the parent function, and it's 0 to infinity. So domain of f inverse equals range of f. In this problem, it's 0 to infinity. But this is a formula that is always in play for inverse functions. The domain is the range. If we swap this around and say range of f inverse, we're just asking for the domain of the original function f. So we go look it up. It was negative infinity to positive infinity. But now that we have domain and range on paper, let's see if it even makes sense. This curve is the inverse function, f inverse of x in green. If I was to say the domain for this, and I wasn't worried about other functions, it looks like it goes from 0 all the way to positive infinity. There's a vertical asymptote right overlapping the y-axis, and that's the reason the domain starts right at 0. So that definitely matches up for what we're seeing here. Then on the graph, the curve does go down forever, so all negative values are part of the range on this thing. It does go up forever, slowly, so are positive values. So that means that extent of the y-coordinates are from negative infinity to positive infinity, completely flipping around from the domain of up above. So that's what our inverse function looks like, and that's the properties it has to have. Any questions at all, folks, on getting through this one? Okay, yeah, go ahead.
Getting the y equals x, how did you get the slanted line again?
This y equals x right here. I pretty much got it from this information somewhere in here. Let me see. There's a formula or a concept. Oh, I didn't see it just yet. Right here. So it says the graphs of the function f of x and f inverse of x are always symmetric about the line y equals x. So I've just pretty much just dropped it right on here. But was your question more about how to produce it or where it came from?
Basically just how to know that that's where you put it.
Oh, gotcha. So yeah, for that line y equals x, pretty much this is the kind of thought I had for this one. It always comes out at a 45-degree line going through 0, but that's just like a random fact about it. But if you want to plot it, you would go y equals x, or let me try again, an x and a y equals x. If you put in 0, it says give yourself a value of 0. So there's 1 point. Put in 1, you would get a value of 1. So there's the next point right here, and so on. So it just produces a line going kind of like that. Your first coordinate, second coordinate just has to match.
Okay. So essentially you're just trying to make a mirror image of that line that's already produced.
Exactly, yeah. The one up here in black.
Okay.
Other questions about that so far? Okay, well, let's take a look at the huge definition up above once again. The definition says b is going to be a real number. It has to be positive. It cannot equal 1. All that information right there is just to give us a bona fide exponential function, like the 3 to the x. So then it tells us that exponential function has that domain and range, a horizontal asymptote at y equals 0. So here's our domain, here's our range, and here's our asymptote. But we observe once we graph any exponential function, and we've done a good number of them, they always pass the horizontal line test, so they're always invertible, and that's how we'll denote the inverse. If we start with b to the x, its inverse would be log base b of x. And then that graph is going to have these features. The domain is going to be from 0 to positive infinity. The range will be from negative infinity to positive infinity. And we take what was a horizontal asymptote, and it becomes a vertical asymptote, x equals 0. So that's what every single logarithmic function is going to do. But now the tough thing about this is, notice this is one function that we are defining purely based upon properties of an inverse function. I didn't write down a formula for log base 3 of x. We just said, well, log base 3 of x is inverse to 3 of the x. So we need some way to start to calculate these kinds of things. And that's what these notes are really about, just becoming more familiar with computation when it comes to logarithms. Before we take a look at those, any questions at all, folks, about the properties above? Okay, so let's take a look at some more information with computation. I would say, and again, we've had some major big formulas throughout the course. We had one where we're talking about end behavior. It was a table with 4 different parts about the leading coefficient and the degree. Then we had another huge theorem about rational functions, talking about the degree of the numerator versus denominators. I would say this is the next really, really big formula. So let's make a big deal out of this one. It is highly important. Let's make it even more important sounding. It is, let's say, vital. That would be a good way to go. It is vital to understand this table. Certain tables or certain theorems or certain formulas are just used so often that it's going to be everywhere. And Alex, it'll come up in quizzes, it'll come up in exams, and this is another one of them. It's basically reminding us what we were talking about with inverse functions. Here we have the exponential function. It's written out as b to the power y. Down below we have its inverse, log base b. But because these are a pair of inverse functions, what always happens every single time is you interchange your x and your y's. We did that already right up here when we were graphing the logarithm. So here's how the interchange works. On the row above, y is the input to the exponential function, so it becomes output to our new function, its inverse, the logarithm. Then on the row above, x is the output of the exponential function, and so that means it becomes input to the logarithmic one down below. So interchanging your x and y's is pretty much the whole challenge on doing some of these computation type problems. In fact, it should feel kind of familiar. Think back in the day, this is an analogy. Think back in the day, way, way back, when you first were introduced the topic of, say, square roots. So this is going way back. Some people might have seen this maybe some like 4th, 5th grade or something like that, if you're a more advanced student. I think my school talked about that stuff in middle school eventually. So when you're dealing with square roots, the issues are you're inverting a function like y equals maybe x to the power of 2. And these are easy to evaluate. Say, for example, if x equals 3, then y would be equal to 9. But then all this got turned around on us. They tell us to evaluate these things like square root of 9. We know ourselves from experience that the square root of 9 is a 3. But what we were really doing when we do these kind of computations, either 3 squared equals 9 or root of 9 equals 3, so we're dealing with a pair of inverse functions. In fact, in section 5.7, we invert functions just like that and got square root functions. And the same pattern happens. On this row, 9 is the input, and it becomes the output on the squaring equation. Down below, here 3 is the input, and it became the output to the square root equation. So this pattern of attack happens all the time if you're thinking square roots, and it comes back really, really heavy on us once we're dealing with something more unfamiliar like logarithms out of nowhere. So let's give this new topic a try. If we have an exponential function, we'll rewrite it into its logarithm form. And if we have a logarithmic function, or equation is the better word there, then we'll rewrite that equation into its exponential form. So looking at this one, definitely that's a logarithmic equation, right? It says log, so it's got to be, it's log to base 5. First thing you'd want to take a look at is definitely the base. The base is your one thing that stays constant when you run through these problems. And same thing with the square root problems. It's just that we don't write the index of 2 typically when we're square rooting something. So I'll put down here, first the base of 5. Then from there on out, we're just putting in information here. I'll delete the boxes in a moment. And here. Anyone see what would be, say, the output in this location? Exactly. We take that whole thing, it is now the output. So if you're a fan of arrows, this would be an arrow to draw. I'll leave the arrow stand on this one. So cube root of 5. Oh, and I did that backwards. Let me try that again. Cube root of 5 would go right there. Then the 1/3 has nowhere else to go. It's going to drop into this location. And it reads now, 5 raised to the power of 1/3 is the cube root of 5. And you know what? That's true. This is really just giving us a new way to look at exponents. In fact, logarithms themselves are regarded as an exponent. If y itself is log base b of x, well, up above, y is an exponent in this table. So the logarithm itself is giving you exponents altogether. So let's take another look at this problem. Another way to think of it is log base 5 of the cube root of 5 is equal to the exponent It's always a good call to think of your logarithm as literally an exponent. It's true. Equal to the exponent that 5 must be raised to in order to obtain cube root 5. That's a lot of oxygen just to say that one statement. But looking at it again, this portion here is saying you have to raise 5 itself to the power of 1/3 in order to get the cube root of 5. So that's just the exponent that's giving you. If the exponent itself is 1/3, then you have to slap on 5 in order to get that cube root. But once we took the logarithmic equation, put it into its exponential form, if you know that this equation is true, the prior equation up above has to be true. And if you already knew the top equation was true, so is the bottom one. These are both just considered to be equivalent forms, 2 equivalent ways to look at the same exact information. So that's a decent comment to make right here. These are equivalent forms. But we're solving equations. Sometimes one form is more valuable than the other. And we'll see that on these notes. Our end goal in this chapter 6 is to look at equations that we can solve using all this information. And so there'll be a decent amount of equation solving coming up. But that's one down. Any questions at all, folks, on getting to our end answer right here? Yeah.
So for the log 5 that you just stated that you just wrote out,
Yeah.
it has to be raised to the power of 1/3. Is that what you're trying to say?
Yeah. So this is an exponent that your base of 5 has to be raised to. So the power was 1/3 in order to get the cube root of 5.
Okay.
Other questions or comments so far? Okay. Well, that's one equation down, and let's try it again. So this one, it's coming in as an exponential equation, and we can see the exponents, the power 0 right there for sure. And it's a true statement, 9 to a power 0 is 1. This is a statement you could never do as 0 to power 0. It turns out 0 to power 0 is undefined. And that's a pretty interesting question on its own. Try to define it. Try to make it equal a number like 1 or something else. If you put it into a logarithmic form, you're going to get something really, really weird. Your base is not going to work out. You would have a base 0, and our logarithms automatically require your base is positive. It can never actually be 0, or it's an undefined logarithm. So 0 to the power of 0 being undefined manifests itself right here as well. But back to this problem, we're going to write it down as a logarithmic equation. First thing you look for is the base. We have a log base 9. The moment we see a base 9 in the exponential equation. So this would be the first thing to write in. The logarithm base 9 of something equals something. But it's really just a matter of take the output, make it be your input, and over here take your input to the exponential function. The input was 0, and that's going to be your output. So this is now a statement that says log base 9 of 1 is 0. Now let's read this out again. Log base 9 of 1, if you're just looking at this part, this is the exponent you have to place on 9 in order to get a result of 1. 9 must be raised to 0, in other words, to get that result of 1, is what this logarithm is saying altogether. It definitely feels like we're jumping through hoops when we make those statements, but it's because we literally are. Even in the square root scenario here, to check an answer, we would say, well, the root of 9, it's going to be the value that you raise to a power of 2 in order to get your 9 itself. Or, hang on, I said that in a weird way. The root of 9 being 3 means that's the number you have to square. Sorry, I said that completely wrong. In order to get the input of 9. And here, the difference is we're just thinking of exponents you put on 9 to get a result of 1. So that's 2 equations down. Let's try another one down below just for that practice. This one came in as a logarithmic equation. So the moment you see that base, write it down again. And I think these ones are a little bit tricky, going from a logarithmic equation to an exponential equation. Because if you go from exponential to logarithm, you're writing down a parenthesis, you know stuff goes somewhere. You can always copy that strategy if you put a parenthesis here. So using that strategy, the input would be the power of 4. And already we can check this out. 3 power 4, well, 3 times 3 is 9, times 3 is 27, times 3 again, oh, that's 4 of them. That would be 81. And so it does check out. This would go down here and gives us a true statement. 3 power 4 really is 81. And that means logarithm base 3 of 81 must be 4. You must raise 3 to the power 4 in order to obtain 81, in other words. Yeah, go ahead.
Will we always have ones that check out properly, or will there ever be ones that are just random numbers put in the new format?
Yeah, there'll be a couple of random number ones, and there'll be some of them even in these notes right here. And so after getting through these kinds of problems, we're eventually gonna have to familiar ourselves with either version of the calculator. So yeah, some nastier ones are definitely coming up. Other questions so far? Okay, so for the moment, we're really just looking at setting these things up and looking at them from one perspective, a logarithmic equation, or another, an exponential equation. But we will have to do some computation, like you were mentioning, and there's a couple things we need ready to go when we do those kinds of computations. You'll see something on Alex and on these notes as well called a common logarithm. A common logarithm is written in this massively confusing way. It's just log x. Now, if you write just log x, this is super context sensitive. In statistics, the base could be e, or maybe in a different branch of statistics, the base could be 10. In our class, a log like this one is always a base 10 logarithm. Let me zoom in the right way. So a common logarithm will come up in this way, and we just have to know it's log to the base of 10. That's not so bad because our calculator does handle log base 10. It is a button, and I saw where this was, right here. There's your log base 10 if you just hit that log button. On the TI-30XA, this is for the Brave, your log button is right here. So that would give you base 10, the moment you click on that key. Then the other really, really common logarithm, the one I missaid a couple times on accident, is the natural logarithm. The natural logarithm is written out this way. Just ln for natural logarithm. And someone asked me this in class once a number of years ago, so I'll give this information back. I had to research this. Someone asked me, why is it ln if it's a natural logarithm? Shouldn't it be nl? And the reason for that is the French were really, really ahead in mathematics for quite a while, and they still are really excellent at it. And they're the one that developed this concept. In French, they call it the logarithm naturel. So it made sense to call it ln. So we go it that way because the French were there first, basically. They planted their flag on that logarithm. Whenever natural log comes up, you're just really doing this. It's log to the base of e, where e is about 2.71. So Euler's number comes up again. But the natural logarithm is, this one's a little bit easier to spot. It's right here. We'll also circle log base 10. And ln is right here. I guess it's not easier to spot. They're right next to each other, but I usually click on that one and I'm lost if I'm looking for log base 10. So what we want to do is, definitely for the purposes of exam 3 and the final exam, we need to be familiar with calculating these things out. So whichever calculator you're using, definitely bring that same calculator with you to the exam. And I would say this one is much easier to use. Definitely use the TI-30XA if you've just taken lots of classes that required it and you're very familiar with it. I wouldn't change out how you're calculating if you like that calculator. The only reason I like this one is you can type everything in one line. It makes it a little bit easier to work through. And let's give this a try. We want to calculate log base 10 of 90. Pretty much calculating log base 10 of 90 is going to go like this. Hit your log key first. It'll print out, practically right in there. The moment you hit that log key, it'll print out log, sort of like that, with a parenthesis. Key in your value of 90. Then close your parenthesis. Here's your parentheses right here to open and close. Hit enter and we'll get a value out. And I happen to have a calculator right here. On this calculator, though, it's not as fun. You have to go inside out following order of operations. On this calculator, hit 90 first. And then I believe I have to hit enter or equals. Then after hitting that, because I want log base 10, I'll hit that button. And I'm getting a 1.954 and some change. Is that about what folks have so far? Awesome, then you're in great shape for doing these kinds of problems on ALEKS and on exams. So let me record, I forgot to say what to round to, but let's go for the nearest 100. 1.95. So this is telling us 1.95 is the power or the exponent that you have to put on your 10 in order to get 90. So it's not a bad idea to just check that out. Let's use Desmos for that check, or not remote desktop. So it says if it's 1.95, don't forget we did round, so it's not directly equal to it, but we should be able to take a power of 10, raise it to 1.95, and be really close to 90. Yeah, rounding to the nearest 100th, we're not too bad off of 90. More decimal places here are just going to get us closer and closer. So you got one down. Let's try another just for the sake of practice. One down below is asking for natural log 3. On this calculator again, hit 3 first and then the natural log button. So 3 natural log. On the other calculator, the one that I claim is slightly easier, that's really kind of an opinion. You would just hit the natural log key first, right over here. Opens a parenthesis for us, throw in 3 and close it. And this one should be about 1.09. Oh, that would round up 1.0986. Let's go with 1.10. Does that look right to folks on that rounding there? Awesome. So the natural log of 3 is 1.10. Now this one's a little bit harder to actually check because, well, it hid the actual base of the logarithm, but you could always think of it as this way. Natural log of 3 is log to the base of e of 3. We said it's about 1.10. So back in Desmos, just for a really fast check again, let's see if we can get that out. You could type in just e, raise it to a power of 1.10, and it comes to about 3. This one's a little bit more accurate. So it does turn out that 1.10 is the exponent you have to put on e in order to get about 3. So we got very close to 3 on that 1.10. Then one last one. Let's give this one a try. This one just says log 74.3. That's all it's telling us. Any volunteers for what we should do on the calculator for a question like that one?
Then just the log button and put that in parentheses.
Exactly. We're just using that ordinary log key, and it'll automatically call up this logarithm. This is stated as a log base 10. So if you use that log key, you're doing the same thing, log base 10. So let's give that a try. We're putting in a random number, 74.3. After typing that in, on this calculator, I have to hit the log key here. So log it, and I get a 1.87. Weird way to do math, right? Just sitting here punching stuff into a calculator, getting values out. But if the function's weird enough, this is a good thing to try out. You have to be familiar how to calculate it with these things in multiple ways. And this would just be one of those kind of ways. Any questions so far? Okay, well, the time we have left, let's see, we have about 6 minutes and some change. The goal is to try to solve some equations next. And this equation here is actually one of our goals. We put this down on paper in section 5.7 and said, the only reason we're doing exponential functions is we need to solve these kinds of equations. So let's make this our last problem. Does that sound right to everyone? Okay, so we'll make this the last for the day. When we come back on Thursday, let's see, we should still finish out all these notes. This is the exam material, but then we're just going to jump right into reviewing for the rest of the time. So we're solving this equation for x. We're going to find multiple ways to solve this equation, but the only tool we have right now is if it's an exponential form, see what it looks like in logarithmic form and hope for the best. So if we're going to logarithmic form, we need to identify the base. Let me fix Microsoft Word, it's bouncing around. The moment you see the base, write out this. Log, throw the base as a subscript, open a parenthesis for the input, and draw in an equals, coming from that equals. Then we're changing from exponential to logarithmic form. That means we're switching where x goes and where 10 goes. 10 is going to become input, and x is going to become the output. So now it says log base 2 of 10 equals x, and that means we have solved it. That's wild, right? This equation does not bend over to any algebraic technique we have at all. It just won't yield. But the moment you define an inverse function, there it is. That's the solution. And that's its most exact form, log base 2 of 10. But now it has a problem, right? What is log base 2 of 10? If you look at your calculators, there is no log base 2 whatsoever. This is also a hint on why there's extra sections on logarithms, properties of logarithms, and all the weird things you can do. Because if we just get stuck right here, inventing logarithms was no use to us at all. So here's a bit of a preview for us. And that's, in our current section, that is the answer in its exact form. But if we want a numerical value, this is what we'll use. A change of base formula can take a log of any base whatsoever, this one's to base 2, of an input 10, and gives us something we can really calculate. Now, this isn't the official change of base formula, but it's the one that you would use if all you're trying to do is calculate something, say like log base 2 of 10. What you would do is take the natural logarithm of the input. So natural log 10 above, then divided by the natural logarithm of the base. This one was base 2. And the way to think of it is the natural logarithm is really useful in this process. The thing that is the input on top stays on top. The base, which is on bottom, stays on bottom. So let's do this computation here. We need natural log 10 divided by natural log 2. And I definitely need a calculator where we can show all that. I try to avoid this calculator because it's kind of rude to use a calculator that we can't actually bring on exam. And also it's not working apparently. Well, that one's not going to work. I'll use decimals instead. So we're not going to use that calculator. Instead, I'll go natural log 10. This works in the TI-30X2S as well. Immediately hit division, natural log 2. And the value should be about 3.32, rounding to the nearest hundredth once again. So I'll put down below, x is approximately equal to 3.32. But let's also emphasize right up here, in this question, this would be considered the answer. We solved it the moment we wrote that out. We were just wondering, did we really solve it? What's the approximate solution? Because once we have approximate solution, we can test this out. Here's our last check of the day. We're going to take 2 to the power of our supposed solution, x, which is 3.32. We should be very close to 10. So 2 to the power 3.32. Well, you know, that does round up. That doesn't look too bad. Let's take another look at this. Natural log 10 divided by natural log 2. It was 3.321. So let's see if we get a little closer by putting in a 1. Yes, much closer. At this point, I'd be convinced that is the exact solution, and that was a decent approximation to that exact solution. And we'll have a couple more that we'll solve when we come back on Thursday's class. But any questions at all, folks, with logarithms so far? Okay, it's a weird but extremely useful topic. We'll see how the actual real uses of it looks like when we get further on into this chapter after the exam. But for the moment, pretty much everything we're going to do from here until next Monday, It's all about the exam. We'll finish off these notes and go right into the review when we come back. Well, have a great afternoon, everyone. If you have any questions, I'll be available down here as usual. Otherwise, I'll see you all on Thursday. Thanks. Certainly my calculator's not working all of a sudden. Oh, well. I guess clicking on it more and more times probably won't fix it.